founding and becoming the CEO of 60 Technologies, was a systems engineer for the CIA. Seriously? That's a first for this group. He was global head of enterprise computing for Morgan Stanley. He was also global head of architecture and engineering for Bank of America Merrill Lynch. Please give a great big welcome to Jeffrey Birnbaum.
All right, let's see if I can figure out that. Is this working? Yes? Good. All right, can everybody hear me? Good. All right, so tonight, what we're going to do, I'm going to tell you a little bit about this really awesome product named AMPS. It's as cool as the design up there. Well, probably a little cooler. I'm also going to talk a little bit about, not so much AMPS, but I want to talk about some performance stuff that will interest you if you're a programmer. How many programmers do you have in the room? Come on, everybody should be a programmer. So, now I started, we'll go with the trivia a little bit. So I started programming when I was 12. Luckily, I never had to give it up, but I still like it. And a lot of what AMPS is everything I learned in all my career, and then a bit more. And of course, the rest of the team brought a totally different ballgame. And Brand Hunt, who's not here, who's the other co-founder, we have debates all the time about who the best programmer is. He's the better systems guy, but I know I'm a better programmer. Don't tell him that. So what is AMPS? How many people in the room know what AMPS is? That's good. Not a lot of you. You're going to know what it is when you leave. If I did my job. AMPS. Okay. So why is AMPS different than? Okay, we're at a meeting of the. Is it MySQL or MySQL? Let's take a guess. Nobody? MySQL. How many people say MySQL? Okay, it's one of those. What AMPS is, it's hard to describe AMPS. AMPS is a messaging system with a database, or it's a database with a messaging system bolted onto it. Take your pick. I don't care. What we're trying to do in AMPS is what I think all the other databases fail to do. One of the key things about a database is you store and query. My attitude is that's so 30 years ago. Today, there's data moving all around. You want to store, query, and subscribe. So not only when you push data to the thing do you want it to store the data, but you want to be notified of those changes. It's amazing. I think 20 years ago, when I first came to Wall Street and was playing around with Sybase, we asked Sybase for this exact capability. Today, they still don't have it. It's amazing. So anyway, however, I think messaging is where it's at. However, SQL is very cool. It's very powerful. So what we said is, let's take SQL, let's combine it with messaging, and let's not do the ordinary messaging thing, which is simple topics. And how many of you develop web applications and use one of these sort of newfangled pub subsystems? PubNub comes to mind, etc. One of those. Anybody? You guys do anything? Come on. Well, anyway, the thing that makes AMPS different than all those systems, okay, is it allows content filtering. What is content filtering? Well, let's say I have a message, a JSON, and it has a bunch of content in it. I want to be able to subscribe to my data, not just the fact that it's a trade, that's the topic, but I want to subscribe to trades where the symbol is in a set of symbols that I'm interested in. Okay, that's a SQL expression. Maybe you could do a Lite expression or something like that. That's what separates what we do at AMPS from everything else. There are some interesting problems that we solve when we integrate a database with messaging. And I'm going to show you a few of those. And then we went one step further. We said, you know, people not only want to do pub sub and have a database where they can query it and get the current state, Okay? They also want to do analytics, which are they want to do summations and groupings and whatnot. So let's say that you're building an order management system. Now I'm being very simplistic here. Building an order management system and you want to aggregate your P&L. Okay? So as the trades come in, you can have a real-time aggregation. Now the cool thing about AMPS is that the idea is that all of this is atomically integrated. So that when you get notified of something, the aggregation that you maybe have will tick at the same exact time. It's not some bespoke system over to the side where you're not sure the trade that just showed up in my blotter, is that in the P&L or not in the P&L? Okay? So, let's just go through some cute charts now. So this is pictorially what AMPS is. It's not one of these, it's all three of them integrated atomically together. So you get a world-class messaging system to connect publishers and subscribers. We'll talk a little bit about the performance of it later. It's a database. It's not a traditional SQL-style database. It's more like an object store that supports SQL. So if we don't have rows and columns and tables, we have what we call SOWs, state of the world. The reason we call it state of the world is because typically the way our system gets used is when somebody connects to the system, they go and get the current state of the world. Like, give me all the trades in the following accounts, and we'll come back with that information. But you can also query at the same time, and we'll talk about that in a second. And then we add some analytics support. So, for those of you that are not familiar with analytics, how many of you heard of a product called Streambase? Okay, so we're not Streambase, and we don't do all of the analytic stuff that Streambase does, at least not yet. But we do a small portion, and it's the small portion that we found to be most useful for the types of users that we've encountered so far. Messaging. Everybody loves messaging. To me, messaging is where we're going in the world. You have so much data, and one of the issues with data is you need to filter it out. I can't get everything. Okay, I only want to get the stuff that I really want to get, and that's where we're going to go next, because that's where content filtering really is different than anything else out there, which is classic messaging systems evolve into oversubscription. Okay, I want all trades. Okay, so I get all trades. So here's my little puny desktop, or maybe my super huge desktop, but the number of trades that's happening every day is going up. So my desktop is getting more and more information. Okay, so then somebody clever says, yeah, you know, I can fix that. What I'm going to do is I'm going to change the topic space a little bit. I'm going to have fixed income trades or equity trades. I'm going to have this kind of trade. Well, the problem with that is now you put a lot of burden on the publisher to publish to the right topic. What you'd rather do is say, hey, you got a trade? Who cares if it's fixed income or equity or whatever it is? Just publish it to a simple trade topic. Okay? Then, me as a subscriber, I can pick out the ones that I want. And those are the only ones I get. Okay? And as we talk about oversubscription being extremely wasteful, not only of bandwidth, but imagine, and I'm going to show you this in a second, if you're getting every message and you need every fifth one, those other four are latency. You're having to parse and go through a couple of messages before you get to the one that you want. Better to not get them, especially if the thing that can deliver them and filter them is really, really fast. Okay? And I'll talk a little bit about performance in a second, because one of the reasons that we exist is performance. Okay? So here's a pictorial of what I just tried to describe. So this is a sequence of messages, and the ones that I want are in green. So if you think about all the trades being published, those are all the trades, but the only ones that I want, like let's say that I'm a trader and I'm only looking at a few accounts. I only want to see the trades in those accounts. The rest of them I don't really care. So I want to discard those. Well, the ones that are in green are going to be latent because you have to get through all the other ones first. Okay? Again, nice picture of what that means. The CPU is pegged because it's having to churn through all this data. Okay? And it's just wasteful, not only on the box, but in terms of everything you do. So this is typically what happens when you have an oversubscription problem. This comes from my experience 20 years on Wall Street. And there are probably a couple people here today that can understand this, which is that these desktop apps that are getting all kinds of data, and as the data increases, eventually you choke the desktop. And you get some trader, it's not really true, you get some trader that screams and wants to know why his app is frozen. Okay? And everything is actually working just fine. It's just information overload, getting way too much data. All right, so how do we solve this? So one of the things, and I'm going to get into a little history now, one of the things that got me excited about this space was performance. Ever since I started programming, I always liked performance and seeing if I could eke out more performance than other people. And in the 90s, I think, I remember having a conversation with IBM about doing this type of problem. And the problem always was that it's too expensive to parse a message comes in, to parse a message, and to actually execute a SQL expression over that message. Remember, it's a little different when you're in a database. I've got this big table, and I can build an index, and I can do all this stuff to make my search fast. But now, you're operating on every message. Every message comes in, you've got to SQL analyze it, across all the content filters you may have, to then send it out. That's a lot of work. Okay? So the challenge is, how do you make that fast? Okay? And we hope at AMPS we've made it really, really fast and really scalable. How we do that is, that's our secret sauce. But another issue was, if you look at a lot of the databases that are out there today, especially some of the open source ones, they're actually kind of clever and kind of cool. I don't want to name any names, but you know which ones I'm talking about. They have large user bases. Okay? They never talk about performance. And I think performance is critical, because as the information flows gain velocity and volume, okay, performance will matter, because lack of performance means latency. Okay? Now you can scale out, okay? And typically people will say, oh, the solution is just to scale out. Okay, but let's think about that for a second. I've got a machine today, right? So I think today you can buy 16-core boxes, and pretty soon you're going to be able to buy 30-core two-way servers. Why are you giving all that up? Okay? Why would you build a system that scales out to hundreds of nodes when you could probably do that in 20 nodes, or 10 nodes, or 1 node? Okay? So the idea with AMPS was, we can scale out all we want, but why not use a box to its maximum potential? Okay? And the reason why most people don't do this is it's hard. The painstaking detail you have to go through with the code is extraordinarily, it's not mind-numbing, it's actually fun, but it's hard to do, so most people don't do it. So this is some examples of some of the content filters that I was talking about. Now, current AMPS, what do? We support XML. So you'll notice that what we've done is we've sort of combined XPath with SQL 92. So we only go as far as SQL 92, SQL 2000, these other ones. They have more and more stuff. But we basically stuck to a small set of SQL that works for us. Okay? We combined it with XPath, because XPath has a navigation, right? It's really XPath locators, locator that we use. It works for just about any type of object. It can be JSON, it can be XML, it can be fixed. Fixed is name-value pairs, so there's really no hierarchy of data in there, but it works just as well. Okay? So that's what the typical expressions look like. So imagine now you have hundreds of these. A message comes in, you have to analyze that across all of those. That's a huge task. Okay? The database. As I mentioned earlier, our database is not a traditional database. We don't have an index. Ooh, that's scary. So what do you do when people come in for queries? So we have databases out there where people have 10, 15, 20, 200 million messages in their database. And that's in a single instance of AMPS. Okay, we've tested as high as 500 million. Okay? So that's not like, you know, your Oracle or DB2 database where billions of rows or whatever. These are objects. Okay? So probably more similar to, say, Memcache, right, that has lots and lots of objects in that access one at a time. Okay? So when we do queries in AMPS, we're actually going to do full table scans. So you say, oh my God, that's really expensive. The trick in AMPS is that we do everything usually in parallel. Okay? And we have a pseudo index. And it's a pseudo index in the sense that it's an index that we update lightning fast. And we don't have to do index rebuilds. Because index maintenance is the thing that kills database performance. So the biggest problem with most databases is that they can't handle high sustained update rates or insert rates because they're always rebuilding their index so they can make the queries fast. So we just said, you know what? If you actually harness the compute power you have in the machine, so imagine I have 30 cores, and I just say, do a table scan. Now, not do a table scan over the entire thing, right? Do a table scan over maybe some specialized cheap index, okay? You can actually go amazingly fast. So in most cases, we'll do a 200 million, scan in less than a second. Okay. Usually, most queries end up being, milliseconds. And actually, the network time to get the results back usually dominate. It's not actually the query time. Now we do this because our database is what we call lock-free. So there's a lot of people that talk about lock-free semantics. Okay, but what that means for us is that we're not impacted by updates. So while you're querying, right, or many people are querying, okay, you can be updating this thing, you can be deleting stuff, you can be going gangbusters. So hundreds of thousands of updates a second, and your query performance really not impacted. Okay, and that's some of the stuff that we built into this thing. And you couldn't do it without these lock-free data structures. Okay, so here is when we compare AMPS, and we think it solves one of the most pressing problems that I saw in the last 10 years on Wall Street, which was, oh, I want to make my app fast, I don't want to go to the database, I want to go to cache. Okay, well, real-time data is slow, so now you have a problem. Okay, so I have a publisher and he's publishing data. Now, unfortunately, the geniuses at Microsoft, okay, so I built these slides, unfortunately I built these slides on Windows, and this is Macintosh, and some of the fonts are off. Okay, so you can't see the detail here, but bear with me for a second. You see some messages flowing, and the labels are supposed to be A, B, C, D. Okay, so the publisher is publishing, and I think he's publishing C. You're getting C on the wire, so you're the subscriber S. Okay, the cache has A and B. Okay, so A is on its way to you because you've done a get from the cache, and I have A and B already in my local cache. So here comes the problem. Which one is the right one? Okay, I know the real-time feed's going to come in everything at C, but what happens when I get A from the cache? I already have A. So is it the right A or the wrong A? Okay. This is the classic problem, one of the classic problems that we solve in AMPS. Okay. So if we take a look at how AMPS does this, okay, there's one thing that you send data to in the AMPS program. It puts it in the database and it delivers it to you. Okay. Now, the reason why people haven't done this in the past is that essentially bump in the wire, right? AMPS. To bump in a wire, essentially. It's too slow. So, in our case, we are bumping the wire, and it adds, depending on your network, microseconds. It could be as bad as a millisecond, right? If your network is bad. But if you use good networks and stuff, it's as good as that. And if you use, kernel bypass technologies for your networking, you can be sustained microseconds. Okay. And again, the idea is that it's a cache that's atomically integrated. So you will always get your messages in the order in which they were published. Okay? So that's a guarantee that we make. Now, the only downside to that guarantee is what if you have two publishers, and we're going to talk about commutative messaging in a second. What if I have two publishers publishing the same data? Okay? The only thing that we can guarantee is that the order in which they've been stored in the database is the order in which you're going to get them. Okay? We also have, I don't have it on here, but we have a transaction log as well, which introduces some interesting things. Transaction log will always be true. So however it's stored in the transaction log is how it's going to be stored in the database and how it's going to be delivered. Okay, these are important concepts. Okay, analytics. Okay, so this is the SEP, complex event processing, aggregation. Again, not a full-blown complex event processing engine. Enough to do what most people want to do. And then, if people want to do more than we have today, we're going to add it. Okay, we're already working on some cool stuff there that I'm not at liberty to talk about today. Okay. So this is the classic thing that we're trying to do. For those of you not in finance, this is classic VWAP. So basically what I'm doing is I'm aggregating and grouping by customer and symbol, taking the quantity and the price, and I'm summing it. So you see that these individual messages for each customer, and a symbol and a quantity, okay, at a certain price, comes in, and then it becomes these two things. So I basically said I'm going to take all the intels that I'm getting, right, and I'm going to produce a value-weighted price, average price. So that's what the 34.70833 is. You do the math, you get your calculator out, do the math, I think that's what it comes out to be. Okay? So what's happening inside the engine, as these messages hit, okay, we're doing this in real time. And this actually, the idea is it's like a SQL view in the sense that we have one table or state of the world, right? Okay, projecting into another, but doing it as an aggregate. Okay? So then you can, this state of the world for this aggregation becomes another state of the world that you could subscribe to. Okay? So as it changes, you could be notified. Okay? As things change. So again, I could be getting all the intels. I could also be getting the aggregated ones. Depends how you want to get it. This is the typical use server use case. For those of you in finance, this becomes an obvious one. The whole reason to have this slide up here is there's one cool thing that we haven't asked that most other things can't do, which is because we have this database, we could do what's called commutative messaging. Commutative messaging is essentially, let's take a trade. And let's say the trade has 3 parts. And I'm responsible for one part, another guy's responsible for the second part, and another guy's the third part. Okay? The trade is stored in the database. Okay? So when I query it, I can get the whole trade. Okay? Let's say this is a swap and it's got multiple legs or something like that. Okay? The idea is that you can publish a delta. So I'm only working on a part of it. I could publish one piece of it. Somebody else could publish another piece. Another guy could publish the other piece. And they all get combined. Right? So we take that delta publish and we merge it into the thing that we're storing in the database. The whole thing. Okay? So we allow you to publish deltas. So let's say that your message is, I don't know, 5K. And all I'm doing is updating one piece of that thing. I can just publish that one piece and it's going to get merged in. And then when the person queries it, they get the whole thing. Okay? It's a very, very cool concept. We also support, although it's not on here, which is delta subscribe. So let's say that I'm only interested in what changed. Okay, just send me, whenever there's a delta publish, I only want to get what's changed. So if one guy publishes the price, another guy publishes the quantity, or some calculated price, I can get just those fields. Now, there's one thing on here that I don't think I've talked about yet. It was the answer to one of the trivia questions, which is focus tracking, or out of focus. What is out of focus? I think it was one of my teasers in the description. Out of focus is an interesting concept that you probably never heard of in other databases. So imagine I have a query that says, I want all orders where status equal open, and they're in the following accounts, A, B, and C. So here comes the real-time flow of all that information. And let's say that actually, let me track. Let's say that I did in AMPS, you could do a query, you could do a query and subscribe, or you can do a straight subscribe. So let's say I do a query and subscribe. So the way that works is that it goes off and does the database query, okay? Delivers you all the data that satisfies the query, and places a subscription at the same time, and it ensures that all updates, okay, after you started the query, come after the query results. So you're guaranteed everything's in order. So you wouldn't see an update, okay, before you got all your results. Okay, that makes it easy for you as an application developer to not worry about the ordering. The ordering is just guaranteed. Now let's say that you put this up on your blotter. I got all my open trades, or orders. Okay? Now, an order goes from the open state to the closed state. Well, you're not going to get that, because that doesn't match your subscription. Your subscription was all orders were status equal open in the following counts. Well, that's a real problem. I now got a trade that's on my blotter, it doesn't match. So one of the cool things we do is when you issue this sal and subscribe, okay, you can say, hey, do out of focus tracking for me. So when a message comes in that used to match, that no longer matches, we'll send you that as an out of focus. So now that event comes to you, and you can take it out of your log. Okay? Instead of you having to place the contra subscription, right, which is, hey, can you also send me all orders where the status is closed? Okay? Nope, you can just do one subscription for exactly what you want, say out of focus, and the coolest thing about it is, as it goes in and out of focus, you get the publish event, you get the out of focus, you get the publish, you get the out of focus, it just keeps going. It's not a one-time thing. It's not like it went out of focus one time, because it could go back. The status could go back to open, right? And then it could go closed again. Maybe somebody's doing cancel corrects on the trade. Okay? So that's a cool concept. All right, some additional features before I pivot to some talk about performance. Okay, we have a transaction log. Transaction log, very cool thing, very high performance. I'll talk a little bit about performance in a second. We're talking about hundreds of thousands, millions of messages a second. Okay, it's incredible performance, and only getting better. We support with our transaction log supports two capabilities. One is replication. So we can do sync and asynchronous replication. We can do as many destinations as you want. I think actually we have a limit at 64. If 64 destinations, you could be replicating data. Okay? I don't know why I can see. The replication uses the same semantics that we use for subscribing. So you don't have to replicate all of your data. You can be selective and say, you know what, I want to replicate only stuff that matches this filter or these filters. Okay? So again, it's selective replication. Bookmark subscription. What is a bookmark? Well, every position in the transaction log, we call it a bookmark. Everybody's familiar with what a bookmark is. You put your marker in the book. That's where you remember where you last were. Same idea in this thing. So let's say that I'm getting a stream of events. Okay, and I'm recording the bookmarks. So every time you get a publish event, you get the bookmark if it was in the transaction log. I can record that. Let's say that I go down and I come back up. Now, in most real-time systems, you come back up, and what happened to all those events? It's not the database, because the database is just keeping the current updated state. What about all the individual events that made that update? That's what a transaction log is all about. So in our system, you can do subscribe with bookmark. So it'll take the bookmark, it'll replay every message that you, quote, missed, and then as soon as it catches up to the real-time flow, it'll cut over to the real-time. We'll actually send you completed your replay portion, you're live now. Okay? Very cool feature. So again, you can build apps where you don't have to do that yourself. You don't have to be, storing everything, right? So some people call that durable subscription. It's a very, very nice feature. Message conflation. So one of the things that we found with AMPS was, in the early days of AMPS, it was so fast, and delivering data so fast, there were lots of traders that were using the system that had slow GUIs. And what I mean by slow GUIs is the GUIs were on older machines, they couldn't keep up. So we basically built this thing called replicas. It's not a replication, it's a replica. So basically it's like a topic that gets updated at some interval, and then you can subscribe to that. And it's sort of like, hey, every 5 seconds, why don't you update this thing, and I'll subscribe to that thing so I can get updates. I can get updates, but I don't have to take them as fast as they're coming, okay? Because I don't want to update that fast, okay? Slow consumers. This is one of the biggest issues we have to deal with, which is that we're delivering data to 500 clients, and we get 20 of them that are ridiculously slow and can't keep up. Well, what do? Do you blow up in memory? How do you deal with that? And most systems have a problem with that. In our system, we go into what an offlining mode. So we'll start offlining for the client to a certain degree, and then we'll finally disconnect it if we can't keep up at all. So as long as we can write data to a disk and keep you serviced, we'll do it. Okay? If we'll queue up in memory first, we'll hit a threshold, we'll start offlining, and then we'll finally disconnect if they just can't read enough data. So we have some entitlement, authentication. The last thing on here is kind of cool. You build a system, you want to deploy it, you need to know how it performs. We actually have internally a full time series database. So it's actually an embedded SQLite database with a schema and the whole thing. We make it accessible through an admin interface through the HTTP. And we collect stats about just about everything that's happening, especially performance stats. Messages per second, client connections, everything that you want to know, we have it so you can actually look at this stuff. Okay. This is your worst nightmare. No. This is an Intel chip, centigrade chip. And it's a pictorial of what it looks like from a NUMA perspective. Okay? For those of you that don't know what NUMA is non-uniform memory access. So if you're a computer scientist, you're building a program, and you run it on a single socket computer, you never deal with this. But, oh, okay. Usually I don't have a problem with projector. However, in most modern systems, you have 2 sockets or 4 sockets. Okay? Herein lies some interesting problems. The latencies that when you talk to memory from one socket to its near memory, or from one socket to the far, we call the far memory, which is the memory attached to a different CPU, okay, it's unequal. Okay, it's no different than when you go to your cache inside your CPU, you get nanoseconds, 15, 20 nanoseconds. And when you go to your memory, it's hundreds of nanoseconds, 115 nanoseconds. Big difference. So cache much faster. Well, when you go across a socket boundary to get memory, it's much more expensive. Okay? So if you write a program that's going to occupy more than one core or more than one socket, you better understand this because your performance can be quite bad. Okay? So this is something we have to deal with all the time. And all I'm trying to do here is give you a flavor for the level of engineering work that we've done in AMPS to make it really fast.
You said it's Sandy Bridge?
That's Sandy Bridge. No?
No.
No?
See, I was listening to or something.
Oh, that's a great observation already. This picture is not fully accurate. So the HW lock that I got this from, it doesn't draw this picture correct. But you're right. Don't worry about that. That even makes it worse. Okay, so this is, okay, so I wanted you guys to walk away and learn something today. Okay, so if you learn nothing else, you're going to learn about AMPS. Numistat. This is a cool little program. You can download it. You can get it. Okay, it runs on Linux. I don't think it runs on Windows. Maybe it runs on Windows. Or does it run on Windows?
What?
Numistat.
Doesn't exist.
Yeah, I didn't think so. Okay, so you got a Linux box. Go find Numistat. This thing will tell you as you run programs what the heck is happening, NUMA-wise. And what you want to do, well, you'll discover for yourself. NUMA foreign, if that number's really high, very bad. Very bad. So you want to watch that number. Okay, I don't think I was running anything when I did this. So looks great. Now, a lot of people talk to us about performance. Now, why did we choose C++? Anybody want to guess? I can't hear you.
No garbage collection.
No garbage collection. Not because it's object-oriented, no way. That's the least reason. Next, come on. Performance. How many of you are fans of Java? How many think Java has got awesome performance? Come on, don't be shy. Java performs pretty good. How many of you guys have heard of something called LMAX? The disruptor pattern. Okay, if you do a web search, Google search, you'll see they talk about how awesome it is. Great performance, kicks ass, shows you that Java can be cutting edge, high performance. So I read this article and I'm like, we do something very similar at AMPS. We think it's one of the things we do really, really well. Why don't I take that piece of code out and I'll make a test that compares us to this disruptor thing. So the next chart I'm going to show you is the result. Okay. So MVFC is multi-producer, multi-consumer. So the idea is that you have some ring buffer, and you're taking multiple producers, right, in different threads, pushing things onto the ring buffer, and you have multiple consumers taking stuff off the ring buffer. And these are various test cases that this LMAX thing runs and report out. So it's the 1P, one producer, one consumer. That's an easy one. Okay? You can see they do pretty good. 69 million operations a second. Of course, we're doing 600 million. Okay? Now, the really, really hard case is really multiple producers, multiple consumers. So in this case, they run a 4P, 4C, and they actually don't even produce a number. And they don't produce a number because it's bad. It really falls apart. And part of the reason it falls apart is the NUMA issues really start to hurt. Okay, because you really start to thrash if you haven't done a good job here. Okay, but we're able to get 48 million operations a second. Now think about that in context. If I told you that AMPS could do 1 million messages a second, or 2 million messages a second, or 5 million messages a second, you can see that the capacity of our multi-producer, multi-consumer queue, right, or ring buffer, well exceeds that. And it has to. Okay, otherwise you could never get the type of performance we're talking about. So anybody that thinks we could write AMPS in Java, forget it. Can't be done. The level of performance we're going after can't be there. And that's not to say that Java is bad. Java does some things very, very well. But in terms of raw performance that we're going after, can't be done. I know somebody's going to come after me. Okay, this is an interesting chart because this talks about code that's NUMA-aware and code that's not NUMA-aware. And unfortunately, this is the dirty laundry. So we had a plan in AMPS that we were going to build it, get the performance where we wanted to with the design we wanted to do, and then we were going to go start tuning for Numinous. Okay? Because Numinous was a problem yesterday, but not as bad. It's a problem today. It's getting worse. Okay? So when Haswell hits the street, so Ivy Bridge I think is just coming out in the server space, but when Haswell comes out, you're talking 30 cores in a 2-socket system. That's a lot of cores. So hyper-threaded, that's like 60. Okay? So you can do a lot of damage. Okay? So we started, and to be honest, we only started this a few months ago. But we ran some initial tests, which is some really basic work in correcting for Numinous. And this is what we're calculating here is a very simple test case where we're doing 100K bursts of messages, and the messages I think are a couple hundred bytes. Okay? A couple hundred byte messages. So the way that this test works is we burst 100K as fast as we can go, right? We wait until the last message is back from AMPS. That means AMPS got it and processed it. Okay? And now we're going to do another 100K. So we just keep doing this in a loop. Okay? And we redesigned part of what we do on the back end to improve what we call the publishing. So in this particular case, there are 50 subscribers, each getting every message. So you have a 100K stream basically coming in and going out, every one of those going out to a subscriber. It's a lot of messages going out. Okay? It's a fan out of 1 to 50. Okay? And you can see that before we tuned for NUMA, we were doing just under 3 million messages a second, or client publishes per second. That's the number we're publishing on the back end. Remember, that's all TCP, so that's a lot of stuff. And when we tuned for NUMA, got it up to almost 5 million, 4.6 million. That's a big jump. And what's more interesting is, you'll notice there's a big fall off there. Well, that's because the runtime of this test, basically the test finishes early. So that's the actual impact. Look, in that case, it's almost 4 seconds of difference on a 20-second test. That's a huge impact. Okay? Next chart. Okay? Similar but more aggressive. So this gets into, you're now pushing the NUMA machine much, much harder. So we've got 5 publishers with the same 50. Now this one's a little different because it's broken up into half of the 50 subscribers is getting half of the traffic, and the other 25 are getting the other half. So it's not a one-to-one. It's a little different. It's a little bit set up. And actually 5 was an interesting number. What we did is took 2 of them, and 2 of them published to one topic, 3 of them published to a different topic. 25 get from one, and 25 get. So it's actually a little bit uneven. It's not exactly 50-50. But regardless, you'll look again at the runtime difference of the test and the actual number. This is, again, now the interesting thing about this chart is this is doing nothing but shutting off half the machine. It did nothing to our code. Okay? All we did here was we took that Numistat, there's a cousin program called Numinous control. What we did is we set Numinous control to basically say, okay, we've got the Sandy Bridge machine, we're only going to run AMPS on half of it. We're going to leave the other half. And it gets better performance. The things that we're working on now, tremendous progress, and if you guys see me present again, I'll show you the numbers. But now we're basically making the whole program completely NUMO-aware, mapping every thread, doing everything that you need to do well. Okay? And the performance is going to be really, really spectacular. All right. This chart is really interesting. Okay. So I told you that we have a transaction log. So if you run AMPS with a transaction log, that is the limiter in terms of performance. Okay? So networks are easy, relatively easy. Getting information in and out, parsing it, amazingly fast. Okay? What's not fast is storing data in a transaction log. Especially when you're doing synchronous replication, where you have to wait till the other side gets it and can't act back. So the reason I wanted to show you this chart was it talks a little bit about the length that we go to at 60 East to drive not only technology, but also performance. Now this, I have to point out what this is. The orange, okay, well, let's start with the yellow. The yellow, okay, here, I think that's yellow, mustard yellow. That is an SSD, okay, where we're doing the 64K byte writes, just hammering. So just as fast as it will let us go, we're just bashing it, 64K writes. So if you think about a transaction log, that's essentially what you're doing. You're just hammering it. Every message comes in, you load it up, go. Okay? So that's what we're doing. The orange line is the same exact thing where we're doing writes. What we have is we have a read job in the back. So what you need to think about here is bookmark replay. So think about it, you're doing a bookmark replay, the performance goes to crap. Look at how bad the performance gets. It really gets spiky in terms of latency. So what's happening here is the reads are impacting the writes in a very bad way. So I came to you and I said, look at my great curve, man. I'll give you, 500,000 messages a second, right, at this latency. Okay, and you say, great. And then all of a sudden you get a phone call, the guy's doing all kinds of bookmark replays, and he's saying, it ain't 500,000, it's more like, 50,000. And it's really, really spiky in terms of latency. Well, that's exactly what's happening here. So we've been working with some companies, okay, and we've been able to produce this blue line. That is awesome. That is where you want to be. That is equivalent to the orange line, or orange graph. So basically, we're hammering reads, and we're doing our writes, and very, very little impact. Okay? That is some technology that we'll be delivering at the end of this year. And we can't really talk about too much now because we're under NDA, but that is spectacular. It's game-changing technology, and interesting, in working with this company, one of the things they told us is they want to work with us because their own test cases can't drive their own storage as hard as we're driving it. Okay? So we go for fanatical performance. We're going to do questions at the end. Okay? Okay? So that wraps us up. Okay? And we're just about to go into questions. So Eric, come back up. I know you guys have lots of questions. If you don't, you will.
Before we move on to Q&A, I want to give a great big round of applause to Jeffrey Birnbaum, CEO and co-founder of 60 Technologies. As mentioned before, this is indeed the 101st New York City MySQL Group meetup. So in honor of that, we do have cognac for everybody. We also have t-shirts for everybody, especially special cut girls t-shirts as well as guys cut. Ladies, excuse me. So they're all here for you to pick up right at the end of the Q&A. So let's move on to the first question. Right here.
Does this cost money? Or is it free?
That's a great question. We can take that offline. Well, I didn't touch on AMPS. AMPS is a proprietary software, so we're not open sourcing the core of AMPS, but we license it. It's not really licensed. It's more like an open source subscription model. So people pay for support. Okay, so. The best answer there is that it's not free. If you want to play with it, download it and try it out, absolutely. We're not going to come after you and say, hey, give us money for that. But it's basically, people can't use this type of software unless they have support. So it's a support model, but we probably are going to have, just like NoDB was here a while ago and took the same type of question about how do you license your stuff, we'll probably have some kind of non-commercial license for people that want to try it out and use it and just don't want to care. We want people to use the software. Bottom line. We think it's awesome. We want you to use it.
Cool. Next question. In the back. You. Yeah.
Sure. For those of us who knew CPS and Replication,
Yeah.
how similar is this?
Kicks its ass. No, so the question is that there was this system, AMPS. When I worked at Morgan Stanley, we had built a predecessor system. Now, I didn't want to get into a history lesson, but and those of you that still work at Morgan, some people still work at Morgan Stanley. I don't want to slag off CPS, but the performance of this thing is not close. It's just not close. Also, there's no aggregation capabilities in CPS, so there's another thing. And we have some additional kind of aggregation kind of stuff that we're working on that's going to be really quite cool, but I can't talk about it yet.
Yes.
Can you speak a little bit more about the entitlements in
Entitlements?
Yeah, in CPS version 2.
Well, we have an entitlements SDK, an authentication SDK. So essentially, you write whatever your entitlement thing is. So we we provide exits essentially and hooks for you to say, yes, this person's authorized for this topic. No, this person's not authorized. And we're actually going into the filtering domain as well. So let's say that somebody can get access to a topic, but only a particular set of the data. We'll actually entitle their filter as well. Now, our users write the actual entitlement module, but we have all of the right hooks. And we have this in production at a major bank now, so we know it actually works well. Right, because they're pretty stringent over there. So both authentication and entitlement. So if you can't do two-factor authentication, you can't log on to the system. Okay? AMPS, when it comes up just generally, if there's no plug-in, it just lets you log in and do whatever you want. Okay?
Would you be willing to talk about generic mapping for the way for data?
Would I be willing to talk about
Making? Yeah.
from what AMPS has?
Yeah.
Absolutely not. No, I mean, part of the reason it's proprietary is because we think that there's a lot of intellectual property in what we've done. I'm sure somebody like Ulrich could recreate what we've done, but it'd be a lot of work. That's a challenge. He's not exactly. Yeah.
The last graph you showed,
Yeah.
just is that like a new hardware innovation?
It's I don't want to say who it is. It's hardware and software. It's not purely software.
He gets Fusion IO.
I can't comment on who it is.
Okay, next question. All the way in the back over there.
I didn't hear anything about redundancy, or maybe I missed it, but how do you handle it when an instance goes down and you want to handle it?
Yeah. So I think I tried to touch on it with replication. So we're pretty traditional. We're not trying to do something like it. For those of you who are here at the React meetup, we're a little bit more traditional than. But the funny thing about, if you look at all those things, you need replication in one form or another. So we replicate at very, very high performance. We think we have a very good acting strategy, and we can do sync and async at the same time, and we can do multiple destinations. So we typically would have, somebody connected to have an AMPS primary, an AMPS secondary, or just an AMPS primary spraying out to a bunch of secondaries. And some of them are WAN over a WAN. And that's where you really want the content filtering to cut down what is actually sent over. So for example, when this came up at the React talk, somebody asked, do you support selective replication? And they don't. Which means if all the data is going in, all the data has to go out to the replicator. Okay? So that usually necessitates some kind of sharding or setup, but we don't do that. We have selective replication.
What context is available when you do message filtering?
What context? What do you
Any
mean?
context other than the message context?
I'm not sure I understand.
Historical context, things that happened earlier, anything like that? Can you use the aggregate information to use as context?
That's a very good lead-in question, and I don't want to get into futures. One of the things that we're doing is we're building some plug-in capabilities so that you can basically write a plug-in that does whatever you want, essentially. So a message comes in, you can use our filtering capabilities and all this stuff, but you can do other things to the message. And you have access to all the aggregates and the state of the world and all that stuff. All the same stuff we would have access to. But I don't know what your special function is that you want to do, right? So we're building a plug-in interface for that type of stuff. Does that answer your question?
Yeah, I mean, performance becomes a question related to
Well, the good news about that is, if you write a plug-in that's slow, it's your problem.
Good for you, bad for me.
No. But then what we'll probably end up doing is having people available to help you write these really, really well, which is the way to solve it. But they wouldn't be our code, they'd be your code. Yeah.
Could you talk about concurrency control?
Did I talk about what?
Concurrency control.
Concurrency control. In what way?
Is there anything special that you do that you can reveal?
Concurrency control. Okay, so we have updates coming in. We have a database. You're doing queries. So we have isolation in the sense that when we're executing a query, it's completely isolated. In the sense that if an update comes in just after you start the query, it's not seen in the query result. Now, because we're a real-time system that's doing pub sub, and if you did a silent subscribe, as soon as you finish the query, you're going to get that update. We're not losing that update. We got those updates. The way we do that, I can't talk about. We do it in a way that's very, very fast and very economical. Yes?
How big are your customers and how much do they use you?
That's a good question. So I can't really talk about customers because most of them don't want us to talk about them. But we have some very, our largest installation we're running at a finance company, and it's somewhere just south of 2,000 instances. Now that's a special case because you say, well, that's crap. I mean, what is the story that it really performs? And it's really what's happening in that instance is lots of different groups are using it for their particular project, as opposed to they're trying to build some big system of intercollected. You could do that. Most people find it better to say, you know what, I'm doing my stuff, and I'm going to have my AMPS instances just do my stuff. And it works just fine that way. If you want to do something bigger, typically that becomes a bigger problem in big places, because you need, like, who's controlling the data and all this stuff. But we have some large installation.
Next question.
Has this been seen in any embedded applications?
Has it seen what?
Any embedded applications, embedded systems?
Not yet. But we have some interest. Imagine, with all the NSA stuff in the news. Let me just say it this way. So my co-founder, if you notice on his bio, he worked at IBM. He worked at IBM through an acquisition. In fact, he ended up in Las Vegas because he went to work for a startup in Vegas that ended up getting bought by IBM. And I can't really say too much about the startup, other than I think he said I worked for the, did some stuff for the CIA. He did something for another agency on big data. So there's some thoughts that we have on sensor networks and whatnot, where we can embed. The client side of AMPS is simple. And in fact, to your point, we're actually open sourcing the clients. The clients will all be open sourced. We haven't put them on GitHub yet, but they'll be there shortly. It's only the server that we're keeping closed source.
Got time for like another question?
So based on your answers to my previous question about redundancy, I'm still a little confused about, well, where does the data get stored ultimately for the persistent part of the data?
It gets stored in a storage medium.
But it gets stored on, so you talk about write performance, right?
Okay, so if you want to have a highly available system, okay, and let's say that your definition of high availability is two systems that both have the data, okay, and their storage devices have the data. So if any one of them goes down, you've got the data and you know it's persistent, okay? So in that particular case, you'd set up an A and a B, okay? Now the cool thing about AMPS is you could set up A to synchronously replicate to B, B could synchronously replicate to A, or asynchronously replicate to A, doesn't matter, right? It doesn't have to be the same, okay? And let's say that all your flow comes into A, it synchronously replicates to B, and what I mean by synchronously replicate is that the client that published the message will not be informed that it's stored until it's in all synchronous replicates. So it has to be stored in B before the client that sent it originally said, store my data. That make sense?
Yeah.
So it's a very simple model. We've streamlined the thing a bit. We do, on the acking side, acking back, we do gapped acks, so you don't have to ack every message, right, which makes it a bit better. So you're just sitting there on the client side, you send out 100,000 publishes, and you get back an ack that says, hey, I've got up to 50,000. So you generate the client sequence numbers, okay, and we act back your client sequence numbers. And we handle, so just so you know, it's much more complicated than that. What happens if A temporarily goes down, you've sent it 100,000 messages, you reconnect to B, and you pick up at, say, the last one you got act was 50,000. You pick up and go to 50,000, but then A comes back up and it's already got those, but it just hadn't acknowledged it yet. We do duplicates. We handle all of that just fine. So we do duplicate control, so you don't end up with duplicates in the transaction logs. That's duplicate detection, that is.
That's all the time we have tonight. Thank you, Jeffrey Birnbaum.